So, Chapter 4 is devoted entirely to the topic of polynomials. May seem a bit much to devote a whole topic to polynomials, but it's actually extremely important, so it's a very sensible thing to do. The thing about a computer, which you probably realize by now, is that the only thing you can really do fundamentally, the only arithmetic you can really do fundamentally in a computer, is the four basic operations: addition, subtraction, multiplication, division. If those are the only things you can really do, then the only numbers you can really evaluate through arithmetic are going to be rational numbers, right? If you're restricted to those operations and you start off with rational numbers, you're just going to get more rational numbers. And of course, the only numbers the computer can represent are terminating decimals in binary notation, so they're rational numbers. Furthermore, if you want to think about functions, suppose you include an x representing the input to the function, and then you look at all the possible things you can do with an x under the operations of addition, subtraction, multiplication, and division, and that'll give you all the possible functions a computer is capable of evaluating. And that'll be the corresponding category of rational functions, right? All the expressions, algebraic expressions involving an x that can be formed from those four basic operations. Now, just as with numbers, every rational number can be put in the form of a whole number divided by another whole number. Similarly, with rational functions, every rational function can be put in the form of a polynomial, right? In other words, using the four operations but really without division, and divided by another polynomial. So every rational function can be expressed as a ratio of two polynomials. That means that polynomials are an extremely important subclass of the functions that you can work with on a computer directly, right? And furthermore, just by dividing two polynomials, and you get everything a computer can do. So it's well worth devoting a whole chapter to polynomials. They'll tell us almost everything about what you can compute on a computer and what functions you can approximate on a computer. We know from calculus, furthermore, that all the elementary functions, they're C infinity, and they have power series expansions, right? Taylor series expansions. So, for example, the sine function can be expressed as a Taylor series. The cosine function can be expressed as a Taylor series. That means that the tangent function can be expressed as a rational function, right? The sine series over the cosine series. There is also, of course, a power series for tangent, but it's not valid in the whole plane. It's only valid in a restricted domain because tangent blows up at some places. We will look at this particular example in much more detail later. We'll see how we can approximate sine using a polynomial of degree 7, for example. We'll just look at the first four terms here, and we'll analyze how accurate that approximation is. And of course, the same idea can be applied to cosine, and then once you've got sine and cosine, you can then evaluate sine, right? So you can evaluate, or at least approximate, all the elementary functions that you learned in calculus on a computer, no surprise, and you do it basically by building up from polynomials. The first thing to talk about is how to actually compute the value of a polynomial efficiently in MATLAB. And it's not as simple as you might think. It turns out there are good and bad ways to evaluate a polynomial on a computer. First of all, let's assume that the polynomial is given to us in this form. There are other forms that you can have a polynomial, but let's take this for starters. So this is where we have a bunch of constants, C0, C1, C2, etc. up through Cn. And then we have powers of x minus a. So x is our input variable, a is a constant. A, for example, might be the center of a Taylor expansion, right? Taylor series expansion. This is the way Taylor series are usually given. Right? So this is a very common way of giving a polynomial. Now, if you were asked to evaluate one of these in high school, you'd probably just start from the left, start with C0, then take C1 times x minus a, and then add C2 times x minus a squared. And that's actually fine. If you're doing it on a calculator, it's not terribly inefficient. It's good enough. However, there is a faster way to do this, which is important if you're going to program it on a computer, and you might have to repeat, this polynomial evaluation millions of times to draw a single graph, for example. And the best way to do it is actually closer to doing it right to left, right? Actually kind of starting on the right and working towards the left. Okay, so let me explain in detail here. So we'll start off by storing the value of x minus a in y, right? And then we can forget about x and a. We'll just use y for everything, right? Because it's just going to be y, and it's going to be y squared, and this is going to be y to the n, right? Also, we'll initialize the value of the polynomial to 0, and then we'll modify that as we go along through the algorithm. Okay, so first what we do is we add the last c value, cn, to v. So now v is equal to cn. Now we multiply v by y, so we get v equals cn times y. Right? So it's starting to look like at least the last term, except we don't have the correct power yet. Now we add cn minus 1, right, the next to last c, and then we multiply by y again, so we get this. So now v is equal to cn minus 1 times y plus cn times y squared. And now the idea is we keep repeating this procedure of adding the next cn minus 1 from the right, and then multiplying by y. So each time we do that, the expression becomes longer, and the powers go up by 1. Eventually, we will add the final c0, and the powers will be up to y to the n on the right. And then we'll have the polynomial we were looking for. Okay, so you see how that works. It's pretty clever. This way, when you multiply, you achieve two things at once. You're not only, well, even several things at once. You're not only multiplying by y in the last term, you're actually multiplying by y in all the existing terms, right, that we've included so far. So you're killing several birds with one stone every time you multiply by y. And the upshot is that this algorithm only requires n multiplications. We only have to multiply numbers n times when you do this. That is, you have to do it once for each term where n is bigger than 0, right? So you have to do the multiplication once for all of these terms. And it turns out that if you do it from left to right, it takes more like twice as many multiplications. Okay, let's look at the algorithm in more detail, more precisely. So we're going to have three inputs. We're going to have x, which will be a number, the number at which we want to evaluate the polynomial. A is also a number, right? It's going to be the number which is the center of the expansion. And c, which is going to be a list of numbers or a vector in MATLAB. But it's not a single number, it's a list of numbers representing the coefficients. And we will assume that the coefficients are given in this order, C0, C1, all the way up to Cn. Right? Note that we don't know, as we're writing the algorithm, we don't know how long this vector is going to be. We don't know what n is going to be. So that's something we will have to figure out. And in fact, that's something I do during the initialization. So first I just set y equal to x minus a. And then we have to figure out what is the degree of the polynomial. Well, the degree of the polynomial will correspond to the length of the vector or list c minus 1, because c actually has n plus 1 coefficients in it because there's a c0 term, right? C0 coefficient. And then finally, when we initialize this algorithm, we can jumpstart the value of v by setting it equal to Cn, because that's the first thing we'll do is we'll add Cn into v. Okay. We will loop n times as I goes from n minus 1 down to 0. Right? We've already handled Cn, so we can start with the next coefficient down, and then we have to go all the way down to 0. So we're going to have to execute this loop n times. And each time through the loop, what we do is we take the current value of v, we multiply by y, and we add the next value of c. Right? So ci, where I is going from n minus 1 down to 0. Notice also that it's more convenient to have the loop do a multiplication by y and then add a c rather than the other way around. I mean, we're always going to be alternating multiplying by y and adding the next c value, but it's better to multiply by y first and then add the c value second in the loop, because then when we get down to c0 we'll be done and we can just exit the loop and we'll have our answer. Whereas if we did it the opposite order, if we added a c and then multiplied by y, then we'd be missing the last coefficient and we'd have to add that in as a separate step at the end. So it's just a little simpler if we start off jump starting it, as I said, with v equal to cn, and then the next step would be multiplying by v followed by adding the next value of c. It works a little bit more smoothly that way, although you can do it either way. Let me add some notes about how to implement some of these things on MATLAB. First of all, about lists. If you have a list or a vector, you can get the ith element of the list in this way. You just say c parenthesis I, right? So that returns the ith element of the list c. Notice it uses parentheses, not brackets or braces or anything, which might be used in other languages. One possible source of confusion, though, is that in MATLAB, indexing is 1-based, which means that the first element has index 1. So, in a list like this, the C0 would actually have index 1, and therefore C0 would be equal to C of 1, right? Not C of 0. And in general, C sub I, the ith coefficient of the polynomial, would be C of I plus 1 in MATLAB, right? It would be the I plus 1 element of the list. Okay, so that's always a source of confusion when working with computer languages. Other languages are 0-based, meaning the first element has index 0, like I think C and JavaScript, I think also, right? Whereas MATLAB and Mathematica are both 1-based. Let's see. Oh, one other thing you need to do is you need to get the length of the vector c. So there's a built-in MATLAB command for that, just called the length function. Length of c gives you the length of the list. What else? Oh, here we have to count down, right? I has to go down from n minus 1 down to 0. And there is the standard notation for a sequence of numbers can be extended in MATLAB to handle this situation. What you do is you put the increment in colons in the middle. So in this case, we would say we start off with n minus 1, that's the first value. So n minus 1 colon, then you put the increment, which is negative 1, colon, and then you put the last value that you want to hit. So in this case, that'll be 0. So you'll use a statement like this to get the sequence of values for I. Also, when you're doing this, don't forget to vectorize the multiplication here. We're going to be multiplying a y value times a v value. We'd like to handle the situation when y and v are both vectors of separate values, right? When you have a whole list of values of x and a whole list of values of p of x, you'd like the multiplication to work right here. So put a dot in front of the star when you do the multiplication here. Let me just make a quick remark about the efficiency of this algorithm. We've already mentioned that this algorithm requires only n multiplications. Compare this to the naive algorithm where you work from left to right, right? You start with C0 and then add C1 times x minus a and then C2 times x minus a squared. Well, how many multiplications does that require? Well, for all the powers of x minus a, you're going to require n minus 1 multiplications, right? Because the highest power is going to be x to the nth, and that requires n minus 1 multiplications, right? To get to multiply x minus a by itself to get to the nth power. In addition, though, each of the terms with powers 1 and higher, so with power 1 through power n, have to be multiplied in addition by their coefficients, c1 through cn. So that's another multiplication for each of those terms. So we got n multiplications for the coefficients, and we have n minus 1 multiplications for the powers of x minus a. So that's a total of 2n minus 1 multiplications in evaluating it the naive way, right? So that's almost twice as many multiplications required. So this is a significant speed up if we can cut the number of multiplications almost in half. Now, before you work on this slide or work with me through this slide, you should complete problem 1 below. That'll be the first homework assignment, which is writing your own implementation of the algorithm we just discussed. Right? So I'm going to assume you have that written, and you'll be able to use it here. We'd like to test it out on approximating the sine function using the Taylor expansion. So you know that the Taylor expansion of sine at 0 looks like this, right? X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on, alternating signs of the terms like that, and they're all odd powers. And we'll see how good the approximation is if we just take the first 4 terms, right, up through x to the 7th. So we can do that by taking our a to be 0, because the center of the expansion is 0, or in other words, we're not subtracting anything from the x, right? And the coefficients are this. Right, this guy here. Now notice that because only the odd terms are present in this Taylor series, you have to remember to put zeros in for the coefficients of the even powered terms, right? So this is C0 is 0, C2 is 0, C4 is 0, C6 is 0. So don't forget to put those in. Now, my version of the polynomial evaluation algorithm is called polyeval, and my inputs are in the order of the first input is the coefficients, and the second input is the x value, and the third input is the a value. You don't have to copy either my name for the function or the order of my inputs, but I assume you have some function with some name, and it does take the same 3 inputs, possibly in a different order. Now what you can do is you can compare this polynomial approximation to sine with the real sine function visually by executing the following commands in MATLAB. Right? So first of all, we'll enter the coefficients as a vector in MATLAB. So C equals this vector of coefficients I described here. And our x's, that is the points on the x-axis that we'll want the graph to cover, will be from 0 to pi. So I'm just going to do like the first wave of the sine function from 0 to pi, and I'll do it in increments of 1/100th. Okay? And then finally, you can plot multiple curves along, in the same graph. You just keep repeating this pattern of x's followed by y values, x values followed by y values. So the first pair of inputs here is the x values followed by the value of the polynomial at those x values. And then the second pair is the x values again followed by the true value of sine at those x values. The first curve will be graphed in blue, the second curve is in orange. So when you look down here, you can see there's an orange and a blue curve. They're almost indistinguishable for the first half of the graph, up to about pi over 2. They start to separate, especially as you get towards 3. But nevertheless, the blue curve, which is the polynomial approximation, it's recognizably a sine curve. It's a pretty good approximation to sine, at least visually. And as I said, it's almost indistinguishable on the first half. But the error does become noticeable as you get towards about 3. So what could we do to improve the accuracy of the approximation? Maybe the most obvious thing is that we could take more terms from the Taylor series. Right? We happen to stop at the 7th power, but we could go on and take the 9th power term or the 11th or the 13th or however many we need to get the curve to be as accurate as we'd like on whatever domain we like. Right? So in principle, you can just go on including higher power terms to improve the accuracy. In this particular case, and assuming that we're really just interested in the values of x from 0 to pi, we could exploit the fact that we have very good accuracy on the first half as x goes from 0 to pi over 2, and that it seems to break down only in the second half from pi over 2 to pi. What we could do is we could make use of a trig identity that sine of pi minus x equals sine of x. This basically just says that if you take an angle and reflect it over the y-axis, it'll have the same value of sine. Right? Pi minus x is basically the angle x after it's been reflected over the y-axis, which is at angle pi over 2. So this says that if you have an angle between pi over 2 and pi, you can take pi minus that angle. That'll give you an angle between 0 and pi over 2. And in that range, we know that this polynomial approximation is very good. So we can use that to evaluate it instead of just evaluating directly sine of x. Right? So if we have a value of x that's between pi over 2 and pi, instead of just evaluating sine x here, we'll evaluate sine of pi minus x instead. And actually, this identity holds for all x, but we're just exploiting it in the range where x is between pi over 2 and pi. Another approach you can take would be to change the center of the expansion of the Taylor series. Recall that this Taylor series is the one you get when you expand at x equals 0. But that's not really the most logical place to expand the Taylor series if what you're actually interested in are the values of sine for x between 0 and pi, right? The natural thing to do would be to expand around the center here, right, at x equals pi over 2. And that way you'd be only going either pi over 2 units to the left or pi over 2 units to the right. Whereas the way we did it, we sometimes have to go as far as pi units away from the center of the expansion. So, of course, we're likely to get a greater error when we do that. So what we could do is we could apply the Taylor expansion to sine, but apply it at the point when a is pi over 2. Now here's, again, the general formula for the Taylor series expansion. We're just going to apply that where f is equal to sine and where a is pi over 2. Okay, so what we get is sine x equals sine of pi over 2 plus cosine of pi over 2. That's the derivative evaluated at a times x minus a to the first minus sine of pi over 2, because the derivative of cosine x would be minus sine x, and then evaluated at pi over 2, that would give you minus sine pi over 2, and so on, right? So I've got that all filled in over here, and then when you actually take the values of sine pi over 2, well, that's 1. Cosine of pi over 2 is 0, so this term disappears. Sine pi over 2 again is 1. Cosine pi over 2 again is 0, so that disappears. So once again, we find that every other term disappears, but in this case, the terms we're left with are the even power terms, rather than the odd power terms as we had in the previous case. This series may look familiar, because this is in fact the Taylor series for cosine, where we've plugged in x minus pi over 2. And in fact, there is a trig identity that says sine x equals cosine of x minus pi over 2. So I could have used that to get the series, just use that trig identity instead, but I prefer to just review how Taylor series work, right? Okay, now what we can do is we can test out our new approximation. I define a new list of coefficients d, right, with the coefficients coming from this series. Again, don't forget to put zeros in this case for the even powers, right? For all the even powers, the coefficients are 0. And then I plotted it the same way. The first plot is going to be the polynomial approximation, that's in blue, and the second plot will be the true value of sine, that'll be in orange. But as you can see, in this case, the two curves are indistinguishable over the entire domain from 0 to pi. Right? So this does give us a much better approximation than the first one did. So we've seen that the first approximation, the first polynomial gave us a good approximation on the first half, not so great on the second half of the domain. And our second approximation was very good, indistinguishable to the eye on the whole domain from 0 to pi. But let's do a formal analysis using Taylor's theorem. So let's recall that our first approximation was based on the expansion of the Taylor series about 0, so it looked like this. This error term will be given to us by Taylor's theorem. Before I get to that, let me just make a quick observation that although at first blush this seems like a 7th degree Taylor series, it's actually an 8th degree Taylor series, right? 8th order Taylor series, because it also has the same x to the 8th term. In the Taylor series for sine at 0, the 8th power term would in fact be 0. So this 7th degree polynomial in fact is identical to this Taylor polynomial of degree 8. So we can treat this as a degree 8 Taylor polynomial, right? So we'll say this is an 8th order Taylor series, and therefore the error term is of this form. That is f to the 9th of c over 9 factorial times x to the 9th, where c is some point between x and 0, we don't know exactly. However, it's easy to get an upper bound for that. In this case, because f is equal to sine, then the 9th derivative of s is actually equal to cosine, and therefore we can say that the error is no greater than the absolute value of cosine c for any c in between 0 and x, right, divided by 9 factorial times x to the 9th. So what's the biggest this could be? Well, the biggest value that cosine can ever take in absolute value is 1, right? So I'll just plug that in. The biggest value that x could take on the interval from 0 to pi is pi. So I'll just plug in the worst case values for c and for x here. And then if you do the arithmetic, you get that the error is no greater than 0.08 ... right? So it would suggest that it's accurate, well, not quite to 1 decimal place, right? So yes, so this is why we were able to detect the error with our eyes in the graph, because it's not really very accurate. It's not even quite accurate to 1 decimal place, right, on the interval from 0 to pi. However, our second polynomial approximation used this expansion, where a was pi over 2. Once again, let me make the observation that this is actually can be regarded as a 7th order Taylor approximation, because the 7th power term would be 0 in the Taylor expansion at pi over 2. And therefore, we can treat this as a 7th order Taylor approximation. Okay, so with that understanding, then we can say that the error term is of the form 8th derivative of f evaluated at c over 8 factorial times x minus pi over 2 to the 8th, right? And now we want to look at this and get a worst case scenario, right? What's the worst this could possibly be when c is between 0 and x? Well, worst case scenario, let's see. So this becomes, let me just point out, f is equal to sine, so 8th derivative of f is also sine, right? If you have sine or cosine, then the 4th derivative is always the same as the original function, so the 8th derivative is also the same as the original function. Okay, so the error here, the absolute value of the error is this, and therefore this is less than or equal to, well, again, the worst case scenario is the biggest sine can be an absolute value is 1. And if x is between 0 and pi over 2, then the biggest this difference could be is just pi over 2. Okay? And now when you evaluate this, you get a much smaller error. Now the error is about 0.0009, right? So it's accurate to about a 1/1000th. And that's significantly better, and that's why it's basically impossible to tell the difference with the naked eye in the graph of the size we were looking at. So this verifies our the conclusion we drew from our eyeballs that the second approximation actually worked much better on the given interval. Notice that this is despite the fact that the second polynomial was of lower degree than the first one, right? Despite the fact that it was of lower degree, it actually gave us a better approximation on the given interval. And that's mainly because we were able to cut the distance we had to travel in half, right? This value x minus a here, right, in the Taylor error formula, is what makes the difference between these two polynomials. In this case, x minus a could be as big as pi, whereas in this case it can only be as big as pi over 2. We cut that distance in half, and when you raise 1/2 to the 8th power, it makes a big difference, right? So that's why we got a much better result in the second case.